Okay, so 37.42 liters. So let's see. Have a helium-filled balloon and it has a volume. So volume is 9.50 and it's at a temperature of 21.5 degrees Celsius plus 273 gives me 294.5, and we have a pressure of 4.25. What is its volume at STP? So I have another volume, so that's going to be my X. So this is 1 and this is 2. Temperature 2 is what? 273. And pressure 2 is what? 1. So we're in a before and after situation. So we go and we find which equation do we need to use, and that would be the combined. So P1V1 over T1 is equal to P2V2 over T2. So 9.5 times 4.25 over 294.5 gives me 1x over 273. And you plug that all in the calculator, you should get x is 270, not 270, 30, what do we say? 4. And the unit is L, big L. Okay. Are there any questions about that? So what we've been discussing for the last week are before and after situations. So here's your conditions prior to, here are your conditions after what happens. And we want to know what happens. So today what we're going to do, we're going to talk about is not a before and after situation. It's at that moment, at that time, what's going on. Okay, so first of all, we're going to talk about ideal gases. So we have real gases, gases that exist, versus an ideal gas. And an ideal gas is one where it doesn't follow all the conditions we expect it to follow. Like a real gas is under different pressures, and it's under different temperatures and volumes and all these things. And they don't behave as we expect them to. So we kind of look at gases like as they are ideal. In the ideal world, perfect world, this is how the gases would behave. So ideal gases really don't exist because gases, they don't stay as gases. We bring the temperature down low enough, we can liquefy the gas. Bring it down even further, then we can solidify the gas. And so you need to know that gases behave most ideally at high temperature and low pressure. High temperature, low pressure is when a gas will act like an ideal gas. So maybe at those conditions, so at high T and low P, our real gas is acting like an ideal gas. Okay, so think of it this way. It's summertime's coming really soon. It's going to be hot, especially here in Texas, so we're going to be under high temperature, and you guys, unless you have to go to summer school, you won't have any school, so you'll be under low pressure. So that is ideally how a gas will behave. So you are ideal gases during the summer when you're under high temperature and low pressure. what we're going to talk about is the ideal gas law, how we expect these gases to behave. And so we can figure out a lot of things with the ideal gas law. And the ideal gas law is PV equals nRT. So how do I remember it? I say perv nert. So PV perv nert. And some people say piv nert, but perv nert's so much funnier. Piv nert. I like perv nert. Okay, so P stands for what? Pressure. And pressure is in atmospheres, but remember, pressure can be in torrs, millimeters of mercury, kilopascals. V stands for volume. Volume must be in liters. No exceptions. Converting, yeah. So N stands for moles. Some of you did not know that on the quiz. So N is the number of moles. And from this, I can take this further to what? Moles. I can take moles to grams. I can take moles to molecules. Okay? R is a constant, and it's called the ideal gas constant. And this number is fixed for this pressure. So in ATMs, this is the ideal gas constant. If we are in millimeters of mercury or torr, then the ideal gas constant is 62.36. If we are in kPAs, then the gas constant is 8.31. So these will be on the board. So you have to look and see what your pressure is in to determine which gas constant you're going to use. All right? And then T is temperature. And temperature is in Kelvin. So let's take a look at this. So the R value is latums, so liters, times atmospheres over mole, so mole K. What's the unit of P? Pressure is what? In this, it's ATM. What's the unit on V? Liters. N is moles. And T is Kelvin. So this is where this unit comes from. That is a unit. Okay? It's 4 units, but that's the unit for the ideal gas constant. This is not a before and after situation. This is at that point in time. How is that gas behaving? So here we go. 5-liter flask. Liters is what unit or what variable? Volume. Contains 0.6 grams. What? Okay, so we have a mass. So it's 0.6 grams of oxygen. At a temperature of 22 degrees Celsius, so T is 22 plus 273, 295. What is the pressure? So P is what we're looking for in the flask. So I look at this, when I have equations like this, and I'll look and I'll see, I do not have a before and after situation. I only have one P, I only have one T. So then that means I have to use perv nert. So PV equals nRT. P is what we're looking for, so that's my X. V is 5. N, I don't have N, so I need to convert my grams to moles. So to do that, I say 1 mole for every 32 grams. What do you guys get? Point what?
Oh, just kidding.
0.01. I'll say 9 moles. So there's my N. Which R are we going to use? Well, we want the ATM, so we're going to use 0.0821. And my T is 295. So put that all in the calculator, solve for X, and X ends up being what? What? 0.092, and the unit is ATM.
If it, sorry, okay, if it's asking for pressure, will it always tell you like in ATM or?
It might. If it doesn't, then I always use ATM. Yep. Any other questions on those?
So volume, you always have to have liters, and then you always have to have moles, but you're not going to be given like you always have to have moles.
Yeah, and remember there's 1,000 liters or 1,000 milliliters in 1 liter. Any other questions on this before we go next? 3. All right. Walkthroughs for you. Now, this next one says how many grams of krypton. So we are looking for mass. Are present in a 600 milliliter container. So my volume is 600 milliliters, but it needs to be in liters. So it's 0.6. The temperature is 1010. And add 273. So we get 1283. And the pressure is 10 ATM. So I look at this and I see there's not a before and after situation, so that means I need to use PV equals nRT. So PV equals nRT. That's just, I mean, that's the way it is, just because there's other T's, like T for time. So P is 10. V is 0.6. N is what we're looking for. R, which R do we use? .0821. And my temperature is 1283. So we solve for N, and how many moles do we get? 0.058 moles of krypton. Yep, so we can't stop there because that's not what the question asks. The question asks for grams. So we have to convert moles to grams. So 0.058 moles, and we need to use the molar mass. For every 1 mole of krypton, we have 83.8 grams. So what is that? 4.86 grams of krypton. We're not done yet, because now let's know how many molecules is that. So I can go from moles to molecules just by using Avogadro's number. So 0.58 moles. And for every 1 mole of any substance, there are 6.022 times 10 to the 23 atoms. So that in the calculator, what do we get? 4.81 times 10 to the 22nd.
Is that right?
Do I have a second on that? 3 point what?
4.9.
I think that's right. 3.49.
Is that going to be like this?
Mhm.
Using the thing?
Anything this week is all fair game for the quiz and last week's. Okay, any questions on that? All right. This walks you through it. Oh. Oh, she was right. So, sorry, I'm recording this. It's 4.77 grams. Oh, no, that was krypton. We did molecules, right?
Dang.
Ew. Oh, no.
That is okay.
Retract.
Show me how to do that on the calculator.
Okay, so what we're going to talk about now is departures from the gas law. So, we say that gases behave ideally at high temperatures, low pressure. So what happens at a high temperature, the molecules start moving really fast. They have high kinetic energy, and they have little attraction for each other, okay? Now when we go to a low pressure, these gas molecules are further apart, and so they have less attraction for each other, and their volume is much more negligible. Their volume is a little bit bigger, okay, because they're further apart. So if we see here carbon dioxide at this temperature, we can see how it deviates from the ideal gas being the black line up there. And then you can see hydrogen. So the heavier the atom is, then the more it's likely it's going to deviate from the ideal gas law. Your more ideal gases are going to be those smaller nonpolar molecules. So what we have is van der Waals equation. And what van der Waals equation does is it compensates for those deviations. So this is just an FYI. This isn't, you're not going to have to solve for this. But you see, because they are actually under pressure, we add back some pressure. And because the volume increases, we take some of that volume out of there. And we get the modified equation to PV equals nRT. Again, you won't be asked to solve for it. Just know that it exists, that there is an equation to compensate for real gas behavior. All right. So certain gases behave more ideally than others. So those are going to be those. The ones that are less ideal are going to be your high molecular weights and your polar molecules and those big, large molecules and weird-shaped type molecules. So if I were to give you krypton versus hydrogen, which one acts more ideal, you'd have to look and see which one's smaller, krypton or hydrogen. Hydrogen, so which one's going to act more ideal? Hydrogen, the smaller one. All right? Hydrogen versus water. Hydrogen, okay? Water versus ammonia. So this is 16, 17, 18 for the mass. This one is 17. So they're kind of going to be really similar, okay? But water is more polar than ammonia, so water would be less ideal. So what we're going to do now is, if I take a canister and we're going to look at mixing some gases. So what happens is, if I take a gas and these gases are all at the same temperature, and their volume's not changing, and we mix them together, their pressures that each one of them give is a total of those pressures. So if I take 0.6 moles of hydrogen, and it's at a pressure of 2.9, and I add it to helium, which is at a pressure of 7.2, the total pressure in the container is going to be 10.1. So this equation is P total, so the total pressure is equal to the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3, all the way up to however many gases are in there. All right, you can just be 2 gases. It doesn't have to be 3. That just keeps going till however many there are. So let's do a problem. I have a mixture that contains nitrogen and oxygen, and if the partial pressure of nitrogen is 7.25 and the partial pressure of oxygen is 426, what is the total pressure? So P total is equal to the pressure of my nitrogen plus the pressure of my oxygen. So 726, 725, 725 plus 426, and we get 1151, and the unit is millimeters of mercury. Tonight on your test or on your homework, and you might even see it on your quiz, is I might say, you have a pressure in 1 atmosphere, 2 atmosphere, and pressure number 3 is in blah, blah, blah millimeters of mercury. So you'll have to convert.
Does it matter which one?
Huh?
Does it matter
I always try to convert to atmospheres, but if it doesn't ask you, you do whichever one you want. Any questions on that one? Okay, so now what happens? I have like 2 slides left. Here's this. Now, to collect these gases, we have to do it over what we call collecting them over water. This says collecting gas through water. I like to say collecting over water because then I can call these cal problems. Collecting over water. So these are cal problems. So what happens is we have this water dish, and we have a jar over the top of it where we're going to collect our gas. So then what happens is we have our test tube, we start the reaction, we're getting that gas, collecting it, and then what happens is we take it and we bubble it up through the empty jar. And the gas forms in that empty space right in here. And that gas, when it's forming in there, starts to push down on the water. And so that's how we can kind of determine how much gas we're getting when we do the reaction. Now what happens is water, when we do this, water is continuously going into a gas. So water is sitting there on the table or wherever, and those molecules get enough kinetic energy and they jump out and they go into the air and they go into gas form. So that's what we call vapor pressure. So we have to take into account vapor pressure of water when we do this. So what happens is you have a table, and the table would look something like this, and you would have vapor pressure of water, and you would have a bunch of temperatures. 19 degrees, 20 degrees Celsius, 30 or 21 degrees Celsius, 22 degrees Celsius. And it gives you a bunch of Celsius, and it tells you what the vapor pressure of water is at that temperature. 17 millimeters of mercury. A 17.56 millimeters of mercury. Okay? So we have to take that into account. Atmospheric pressure, that is our total pressure. P total. Okay, so atmospheric pressure is going to be our vapor pressure plus the pressure that we made, our water vapor pressure plus the pressure from the gas. When you see these problems, we'll talk about what's the dry gas. That's just the gas without the water. Okay. A sample of nitrogen is collected by the downward displacement of water from an inverted bottle. What's the partial pressure of the nitrogen at 20 degrees Celsius if the atmospheric pressure is 752 millimeters of mercury? The vapor pressure of water is 17.5 at 20 degrees Celsius. So this has told you. You don't have a chart to go look at. It's told you what it is. So atmospheric pressure is my pressure total. And that is 752 millimeters of mercury. Because it's collected over water, I know that this is a cal problem, so I know that my P total is going to be my P of my gas plus the pressure of my water. So my total is 752 is equal to the gas, that's what I want to know, is the dry gas, plus water, which is 17.5. So what is the dry pressure of my gas? 742? 752 minus 17.5? Why did we divide?
Why'd you guys divide?
Well, then when you add it to the unit, yeah, then you have to divide it by 17.5.
You're subtracting.
Silly goose, are you kidding me?
Oh.
734.5.
Because no, I was trying to do it like 17.5x.
734.5.
Okay, I understand. Come on now. Oh my goodness.
Oh, makes sense. So what is it?
734.5 millimeters of mercury.
Were you about to do the like X? Okay, that's not it. That just makes me feel better.
Okay, are there any questions over the cal problems?
Yes.
Yes?
I get it now.
Yeah, it said,
Of course I get it.
it said what is the partial pressure of the nitrogen gas at 20 degrees Celsius?
Uh-huh.
Can you just ignore that?
Okay, so that's where, if we had a chart, we would go look at 20 degrees Celsius, but it told us that water at 20 degrees Celsius is 17.5. Okay? So if it didn't tell us, then we would go look at that chart. Any other questions?
No.
All right, well, you have 10 problems for your homework.